This project is about the development of an artificial neural Hopfield network to enhance memory recall. Let's get started. Whoops. Okay, there. Introduction. So first and foremost, what do we know about our memories? Well, memory recall is known as a partial to total loss of information in memory systems, which may involve recalling distorted events or details. This error is primarily due to interference from concurrent overlap. When one memory is accidentally linked to another to produce a connection between two independent situations, memory traces overlap. Let me see. Yeah, so there were several theories developed regarding the pathway of recall. The first one, the standard model of systems consolidation, suggests the hippocampus plays a role in determining recall, usually by saving and then transporting a memory or by binding it to the extra hippocampal sites. The hippocampal indexing theory explains the role of the hippocampus in encoding and recovering memories. Furthermore, more recent research suggests memories are less dependent on the hippocampus and more so on the anterior cingulate cortex, or the ACC, and the retrosplenial cortex, or the RSC. So what is our objective? The ultimate goal of this project is to optimize memory recall through specific inputs to an artificial neural network. The hypothesis is that the ACC, or anterior cingulate cortex, can gauge the external inputs to the network to optimize memory recall. So how do we build an artificial neural network? Well, to preface, the original goal of the neural network approach is to create a computational system that can solve problems like a human brain. A simple neural network includes an input layer that you see in green, an output or target layer in yellow, and in between a hidden layer in the blue. The layers are connected via nodes, and these connections form a network, or the neural network of interconnected nodes. So my experiment used a specific type of neural network, which is a Hopfield model. This model provides an optimal example for understanding the processes of human memory because they can store memories in neuronal activity patterns. And unlike the last slide, this network connects every input with one another. The energy function below defines the flow of the Hopfield model or network. The goal of these configurations is to reach a minimum energy level as seen in the graph to the right. So funneling our network, where did we get with it? What are the results? During initialization of the model, every input represented by J was set to 0. I used the following algorithm to store memories. My loop of code only stopped when all values in the matrix reached an energy minimum. After running the data through MATLAB, all of the results came out as identical, indicating that they all reached that energy minimum. And here, next steps, we have memory retrieval. Beyond memory storage, there needs to be a way to recall information. So revisiting the energy landscape of a Hopfield network, mind you that when storing memories, I worked to make sure every attractor reached a minimum level state, but the goal of this project is to not only have all memories at a minimum, but also make sure that they're stored in the green area or the basin of attraction. In this landscape, you can see that there is a possibility of reaching the minimum, but not the basin of attraction. So like, how do we deal with this? Like, how do we make sure that we can fulfill both of these constraints? Well, in order to fulfill both of them, I plan to use the following algorithm, which updates the attractors. At every step here, the network evolves towards states with decreasing energy until the desired minimum level is reached. This net will have the ability to restore a corrupted memory to the spot that most closely resembles the input. This reverse process is called associative memory because it restores memory through the resemblance of two inputs. That way, we'll be able to retrieve memories without overlapping them and be able to retrieve memories as they are. Here is just some code that I used in order to store memories. This was done on MATLAB. I defined the variables for my value. I defined the matrix for a set of 3 memory configurations to store in the network. I then computed the epsilon values until all of them were 0 or until all the values were 0. And this basically just continued as a loop until our data set had all values at that minimum energy level, and then it ended. So let's go to the discussion. Where can we go next? So before we get too ahead, there are a few limitations in the study. In order to accurately predict the strength of the Hopfield model, a larger matrix and data set are needed to observe if overload affects network performance. Additionally, a central clock will need to be designed to maintain synchronization of units for accurate outputs of states in memory retrieval. This endeavor will be especially difficult as it is currently unknown how this clock could be implemented in the brain. Some implications, on the other hand, the success of storing memories in the Hopfield model and the further development of memory retrieval has prospective implications for neurodegenerative treatments and different diseases like Alzheimer's, Parkinson's, and dementia. The Hopfield model can be used to simulate the effect the brain-machine interfaces can have on brain-like circuits, and then to determine the ability of the brain-machine interfaces to aid in memory retrieval. So far, there's no optimal memory restoration method. By training the data and memory retrieval synchronously while qualifying connectivity, rate of memory improvement, among other parameters, the potential for full memory recovery is achievable. For the conclusion, the results show how to store memories in the Hopfield model. The success of storage and the rule for retrieval holds strong potential for recovering memory cues, though it is not without its faults or its limitations. Testing a much larger data set and successfully coordinating synchronous updates for units will need further work. Gauging the external inputs to the attractor network to optimize memory retrieval also requires additional investigation. But this ability to recover memories holds strong implications for neurodegenerative technologies, and with more work shows much promise for technology and society. And I think this is just a really interesting approach rather than the typical, targeting different biomarkers for Alzheimer's disease, rather than going to the typical like drug development route. I feel like this technological or physical or mechanical way is something that hasn't been explored, but has a lot of potential for these types of diseases. Knowing that Alzheimer's is like one of the leading causes of death in older people, and it doesn't have a solid or a cure for it. It only has medicines that slow down the decay that happens to a person during Alzheimer's and then later dementia. Well, before I end, I have to give a really big thank you, first and foremost, to my mentor, Dr. Tivani, for making this project possible. It was not always easy to understand and formulate the code and algorithms, but through her deliverance and providing the best resources and research, I was able to comprehend what I was doing. To the rest of the Talaria officers, thank you for working so hard this summer to get us paired. It's not always easy to get remote research opportunities, but I really applaud the effort you put into this endeavor. And for everybody else, thank you for listening, and thank you for listening to my presentation.
Do you need help?